So this morning I want to give, well, I say a technical introduction to Bitcoin and cryptocurrencies. So we'll talk about that Bitcoin is, some people call it a cryptocurrency. That's a currency that uses cryptographic techniques to ensure that we have the features that we expect of a currency. We're going to focus on Bitcoin. There are others, but Bitcoin's the most popular. We'll mention some others towards the end. So we try to explain, well, what is Bitcoin? But I'm going to focus mainly on the technical aspect of how it works. And towards the end, we'll go through and look at some of maybe the financial aspects, what it's worth, how to make money, how to lose money, and some other issues. So to understand Bitcoin, we need to know something about cryptography, because the way it relies on cryptographic techniques, so we need to know the basics. But we can get away with going through a lot of details. So the next few slides, and the handout includes these slides, and on the back of the handout there's just a printed sheet, started with assumptions, which is a little bit more detail of the first few slides. Some people have seen it before. They've sat in some of my courses and we've gone through this before. But let's look at the cryptographic principles that we need to understand Bitcoin. And we'll not look at all the things that I present in these next few slides, just go direct to the ones that are needed. So we're clear on the assumptions. Actually, I've got... And we've mentioned this before, but not in much detail, that cryptography, to encrypt things, we've got the original approach called symmetric key encryption. I want to encrypt some data. I use a key, a secret key. I encrypt it. I send the data to you. You use that same secret key to decrypt. That's symmetric key encryption. This is just some notation that we may see. We don't use that in Bitcoin. Don't care about that today. So there's another form, public key cryptography. And we did see that a little bit last week, where we used email encryption using public key cryptography. So let's say about this, because it is used in Bitcoin. Each user has a pair of keys. So everyone in this room has, let's say you have your own key pair. And one of them is called the public key and one's called the private key, PU and PR. As the name suggests, the public key, you can tell anyone. You can make it public. The private key, you keep secret to yourself. If you don't, then it's no longer private and it's no longer secure. And the algorithms in public key encryption are such that if you encrypt with one of those keys, encrypt some data with one of those keys in the pair, then you can only decrypt if you have the other key from that key pair. Okay? Not all algorithms have that, but that's common. That in either direction, if I encrypt with a public key of a particular key pair, I can only decrypt using the corresponding private key. And similar the other direction, if I encrypt with a private key, I can only decrypt with a corresponding public key. Okay? So that's common with some algorithms. And we use those features to provide confidentiality and also signatures. So what do we mean by them? Confidentiality, I want to keep my data secret. I want to send it to someone so that no one else can see the contents. Only that recipient can see it. So I'm user A. What I do is I have my message M, and I use the destination's public key to encrypt. Okay? So I want to send Sam a message confidentially so that someone else cannot intercept. What key do I use? The public key of who? Of Sam. Okay, so if I want to send to Sam, I encrypt using Sam's public key. Okay, so confidentiality, encrypt the message using the destination's public key. Okay? So another test. You want to send a message to me confidentially. What do? Encrypt using, so yeah, correct. So you encrypt, and when we encrypt, we use a key. Which key? You want to send it to me. You use the public key of who? Of Dana, of you, of me, or of me, okay? So that's all we need to know. How that works, well, the algorithms that implement that, you need to study them to see why it works, but it works. You encrypt with the destination's public key. The only person who can decrypt is, of course, that destination, because only they have the private key. Okay? So that's the concept. The other feature, and commonly used public key cryptography, is to provide a signature. Here we don't care if someone sees the message. What we want to be sure that a particular person created that message or generated that message. And we can verify later that it came from that person. We want to sign something. That's the idea. Here we use the keys in the opposite direction, and the person who wants to sign something encrypts the message using their private key. I have a message, I encrypt it using my private key, I send it to whoever, to everyone, to a particular person. Can anyone read the message? If I encrypt with my private key and send it to one person and others intercept, can they see the contents of the message? Yes. Why? Yes, because the public key is public. That is, I encrypt with my private key, I send to someone, and someone else intercepts. To decrypt, they need my public key. And by definition, my public key is known by everyone. It's public. So this does not provide confidentiality. People can still see the message. But what it does do is proves that this message came from me. Because if it decrypts with my public key, it means it must have been encrypted with my private key. And the only person in the world that has my private key is me. Okay? So that's the concept of a signature. To sign something, you encrypt with your private key. Anyone else can verify it came from you if they have your public key. Okay? What if you want to sign a message and make sure no one else can read it? What would you do? Again, you want to send me a signed message and you don't want anyone else to read it. What would you do? Encrypt the message with, when we say by a private key, always identify who. Everyone has a private key. Encrypt the message with whose private key. You want to send to me a signed and confidential message. What do you do? You don't have my private key. If you did, it wouldn't be private. Yeah, if you want both of these features, signature and confidentiality, just use them both. That is, encrypt the message with the destination's public key for confidentiality, and also encrypt using your private key for the signature part of it. So they're two separate features, two separate operations, and we can do both of them if we like. In Bitcoin, we're mainly going to use the signature part. So what you should remember is that if you encrypt a message with your private key, we say it's signed. And people can prove it came from you. Okay? And that's all we need to know at this stage. There are many different algorithms for doing this. They're just some of them, or not many. These are the main ones. We're not going to focus on the algorithms, just the concept. Any questions about signatures? Of course, everyone needs a key pair. We can generate them. And then you need to distribute public keys Well, let's say we have a way to do that. Then we sign with our private key. Another thing that's useful, very useful, and is an important part of Bitcoin is hash functions. Everyone knows hash functions from some data structures course, maybe. You've probably seen hash functions in programming when people talk about data structures. But we use them in cryptography as well. And without going into the details, what can we say? A hash function is something that takes an input of any size, of any length, and produces, with a cryptographic hash function, produces a fixed, usually small output, which is effectively random. Okay? The output is a random number or a random sequence of bits. And if we take the hash function of a different piece of data on input, we'll get a different output. Okay? You hash one file, you get some random number as an output. You hash a different file, you get a different random number as output. Okay? And these outputs are usually small, hundreds of bits. And it's a one-way function in that if you hash some input and get a hash value as output, that's going one way in the function. Going back, taking that hash value and finding the original input is hard or impossible. Okay? That's given a hash value, so let's summarize this notation. A hash function is some function that takes some variable size input, some message m as in, and it produces a fixed size, usually small output value called the hash value or the hash. And I denote that as lowercase h here. So the hash of m equals h. If you know the hash value h, you won't be able to find the message m. That's this one-way function property. That's this second one. If I give you the hash value but say nothing about the message, it'll take you forever, so practically impossible to find the original message. But if I give you the message, it's easy to calculate the hash value. Easy going in one direction, hard going the other direction. Some other properties. If I have a hash value, well, we won't cover this. We'll simply say that two different messages will always produce two different hash values. It's usually true in practice, but maybe in theory it's not true. Okay? But for the cases we'll deal with, it will assume it's true that if you hash two different messages, you'll get two different hash values. Okay. Some examples you may have seen in different occurrences at different places. MD5, it's a hash function. SHA, the secure hash function. SHA-1, and there's SHA version 2, and some other hash functions. Okay, so there are different hash functions. And we'll assume that they have these properties of one way only and two different inputs to get two different outputs. Where have you seen hash functions? Apart from on this slide, where maybe you've come across them in the internet or in computing. Where? When you download the file, you can check that the file that you downloaded is the correct one. Why would it be incorrect? Maybe the download didn't download everything, okay? Or maybe there was someone malicious in between you and the web server that changed it along the way. So you go to some website to download a file, and on that website they'll publish the hash value of the file. Okay? So there's the file, the link to the file, and the hash value, the MD5 or SHA hash. What you do is download the file. Once you've downloaded the file, you calculate the hash of the file you have and compare it to the one on the website. If they match, it means you've got the same file that the web server had. If they don't match, if the two hash values are different, it means the two inputs were different, which means the file at the web server and the file you have is different. Okay? So you'll see it with that purpose of That's mainly for error detection, to check that the file you received has no errors in it. Some examples. I have 4 files on my computer, EX1 through to EX4. So the first 2 are text files and the other 2 are binary files. Looking at the first 2, they are 23 bytes in length, same length. Okay? Are they the same file? Well, how do you know? You need to look at the contents of the file. So EX1 is just a text file with a simple message. Hello, this is a demo. So it's just an ASCII file. Length is 23 bytes. Okay, there are 23 characters if you include the new line. We can calculate the hash. And I have a program called SHA-256-SUM. A hash is also called a checksum. So the program, SHA is the algorithm. There are different variations of SHA. There's one that produces a 256-bit output. Okay, so if I use this program on that file, it will calculate the SHA hash value. There it is. Okay, this long in hexadecimal. If you convert that to binary, there are 256 bits there. That's the hash value of the contents of the file. Not the file name, the contents of the file. So this program took this text, applied the SHA algorithm, and produced the 256-bit hash value. And example 2, is it the same as example 1? Oh well, if you can't see, let's calculate the hash of example 2. Different. If you notice that it's the same text except I change one letter, is to it. Okay, so 2 different inputs produce 2 different hash values as output. Do you see any structure in these hash values? Patterns? They are effectively random. Okay? There's no relationship between these 2. Even though the inputs are very similar, there's only 1 byte that differs in those inputs. The outputs are completely different and random. Okay, so that's what we'll assume. Hash functions produce random outputs. If we hash the same file again, what will the output be? If I calculate the SHA-256 hash of example 2, what will the output be? It will be the same. Okay. When I say random, it's not just generating a random number, but it produces a random sequence of bits such that if we take the same input, we'll always get the same output. Okay, that's important. So these 2 are the same because the input's the same, but when the input's different, we'll get a different output. EX3 and EX4 are binary files, just larger, about 2 megabytes. They have files, and so of those 2 megabytes, I copied the first file and I changed just 1 byte. Of those 2 million bytes, I changed just 1 of them. So all of the bytes in these EX3 and EX4 files are the same except 1 of them. Let's see. This is a bit out of scope, but I just show you that the binary or the hexadecimal of that file. What I'm showing is the first 64 bytes of EX3 and then the first 64 bytes of EX4. And in hexadecimal, it doesn't make much sense. It's a binary file. It's an application, actually, I think. If you look closely, 5735, 5835. The only difference of all these bytes in the file is this one here. It's 57 and here's 58. Everything else is the same. 3447, zeros. And if you went through all the 2 million bytes, they're all the same except this byte. Okay? I just changed one byte. And just to show that our hash function works, again, hash of EX3 is this C1, 1, C7, da, da, da. Hash of EX4, which is almost the same as EX3, is completely different. Okay? Just random hash values with different inputs. Questions? So really for now, all you need to know is that to sign something, we use our private key. And hash functions produce random outputs, and for two different inputs will produce two different outputs. And if I give you this hash value, 1BEAF, I tell you this, you will not be able to find the original file. It's impossible in this case, or practically impossible. That is, if I just give you the hash value, go and find the original input. We say that's practically impossible to take the hash and find the input. I think that's set us up for Bitcoin. But digital signatures, we've basically said, in practice, digital signatures, we said we use the private key. Or in practice, we hash the message first, but not important, I think. That's random numbers, we're assumed that we've got good random number generators. There's an entire topic on how to implement random number generators in a computer, but that's not for this. So there's nothing more to say. Attacks, again, that's not relevant. When I say that we have a private key, we assume that that's kept private. If you've got a private key and you tell someone else, then all of the conditions that we're building Bitcoin upon will not work. Okay? It must be kept private. If it's made public, then things fail. The security of things fail. That's the assumption. But I think those points are not relevant to go through at this point. Let's get into Bitcoin. And if there are questions which come back to these cryptographic principles, we'll return to them if needed. What I'll do to try and introduce Bitcoin is go through a simple example of how we transfer money between people using a bank. And then look at, well, how do we do it using Bitcoin? Because we'll see that Bitcoin tries to be a decentralized currency, a decentralized payment system, really. A payment system is something that we can transfer money to someone else, pay someone. With banks, we can think of them as centralized systems. So the bank is this central point which all our payments go via. I want to transfer money into your account. Well, that transfer is actually via banks. Okay? So I use my bank account to transfer it into your bank account. The bank plays a role there. Bitcoin tries to make that decentralized, that there are no banks, but I can still transfer money from me to you. Okay? So we want to see how that works. So how do we pay people using normal banking? And we'll just use a simple example. And again, let's say we all have an account with one bank. Everyone here has an account. And we want to pay or transfer money between people. I want to pay for something. Then how does it work when we use a normal bank? Well, the bank keeps track of your account balances. Okay? The bank knows how much you have in your bank account. And they keep track of transactions. So if I transfer 10,000 baht to someone else's account, that's a transaction. Okay? It comes out of my account and goes into your account. Okay? So the bank has a record of that transaction, and from that transaction they know that my balance has gone from 100,000 down to 90,000, and the destination's account balance has gone from 10,000 up to 20,000. Okay? Transactions change the balances. So from a transaction point of view, we can think there's always an input account. Transfer from my account is the input. Then an amount, how much I want to transfer, and the output account, who am I transferring to? And if you use online banking, that's the basic setup. You say, okay, from my account, transfer 10,000 baht into this destination account. That's a transaction. It's all done via a bank. When we use, in this example, so it's a centralized system in that the bank is involved, and the bank is the one that keeps track of these transactions and keeps track of your account balances. Can we do it without involving the bank? That's what Bitcoin tries to do. Try and do it so that I can pay someone and have the same features that people can't cheat. Okay? It's no good if I pay someone or I say, here's 10,000 baht, and then sometime later someone comes back and says, no, you didn't send me that 10,000 baht. Or I've got an account balance of 5,000 baht, that's my current balance, and I try and pay you 10,000 baht. That shouldn't be allowed. I've only got 5,000 baht, I shouldn't be able to transfer to you 10,000 baht. Or I have 5,000 baht in my account, and at the same time I pay one person 3,000 baht and another person 3,000 baht. If my balance is 5,000 and I try to spend more than 5,000, it shouldn't be allowed. Okay? A bank keeps track of your account balance and those transactions and prevents that from happening. Okay? A bank won't let you spend more than your balance. So what Bitcoin tries to do is create a decentralized system with no bank involved, but still has those features. Let's go through and look at transactions, and then we'll move and see how that's implemented. So in a normal banking situation, we may view it, we've got three people, three accounts. Okay? Me, Tanarak and Pakini, okay? Different faculty members. We want to transfer money between each other. And let's say to get started, we each have the balance according to the first row. I have 0 units, baht, whatever, dollars, doesn't matter. Tanarak has 30 and Pakini has 45. That's the opening balance. And then over time, as time increases, we make transactions. We transfer money to each other. So in this example, Tanarak transfers 5 units to me. As a result, his balance goes from 30 to 25. Mine goes from 0 up to 5. So the blue one is the transaction. Input account was Tanarak, output was mine, the amount was 5. Then sometime later, so the rows keep track of the balances. Pakini transfers 8 baht to me, mine goes up, hers goes down, and then maybe another case. Here's a special case we don't often see. Tanarak transfers 5 to me and 10 to Pakini in a single transaction. Well, with banks we don't normally allow that. But we'll see in Bitcoin that's possible, that you can have a transaction and you can specify different destinations. So we'll see that come up. That is, of course, Tanarak's account balance will go from 25 down to 10. 15 is coming out. 10 of it will go to Pakini, so hers will go up to 47, and 5 of it's going to me, so mine will go up to 18. And then a last one I transfer. So the balances at the end are 7, 21 and 47. Okay. We'll try and go through and see how Bitcoin implements such transactions and look at some of the issues. Any questions on what I've shown here? This is just for a normal bank. Easy? Okay. What if I want to create a transaction to pay Pakini 10 units, 10 baht, whatever? What happens? What does a bank do? If at the next step I try to transfer 10 to someone, the bank or the system would prevent that from happening. It would reject the transaction because I only have a balance of 7. If I try to transfer 10 to someone else, the banking system will reject that transaction. The bank is the one that keeps track of these transactions. Okay, so the bank has a record in their computer system of all of these transactions so that they know if these were the starting balances, these are the current balances. It's easy to calculate. Okay, you just look at all the transactions and you work out what the remaining balance is. That record of transactions is sometimes called, or is often called, a public ledger or a ledger. A ledger is just a record of these transactions. We'll see that Bitcoin looks at transactions, so we could present this information from a transaction point of view. Look at the blue lines. 5 from Tanarak to Steve. I could write that as a transaction 1, TXN, meaning transaction. In was Tanarak, that was the input account. Out, it went out to me, the amount was 5. So I just summarise that transaction. Transaction 2, from Pekini to me, 8 units. That was this one. Okay, so the blue lines I've written as 4 transactions. Transaction 3, in from Tanarak, output 1 was me, 5 units. Output 2, Pekini, 10 units. So we could have a transaction with 2 outputs or multiple outputs. It turns out in Bitcoin you can have a transaction with multiple inputs as well. So if we know the opening balances and we have this list of transactions, then we know how much everyone has. How much do I have at the end of these transactions? Well, from that I start with 0, out to me 5, so plus 5, out to me 8, so I'm plus 13, out to me 5, I'm 18, in from me, that is, I'm spending, minus 11, so 18 minus 11, I've got 7 units at the end of these 4 transactions. So we can, if we have the list of transactions and we know the opening balance, then we know the current balance. And what we'll see in a decentralized payment system is that, and in Bitcoin, we record all transactions that ever occur. And there's a public list of all transactions. So if everyone knows this list, then everyone can work out what everyone else has. Okay? So from this information, Steve, Pekini and Tanarak all know what each other have as their current balance. Therefore, if I try to send 20 baht to Pekini, she will not accept that, because she can determine that my current balance is only 7 baht, or 7 units. So if you know the list of transactions, you can provide these features of a bank that is working out who has what and stopping people from double spending or overspending. Questions? Nothing about Bitcoin really yet, just about banking or payments. But we'll see that. All right. Let's extend this. What about these opening balances? Well, we can treat them as special transactions. Where does my balance, or where does Tanarak's balance, opening balance of 30 come from? Well, let's treat that as a special transaction. Let's say all users start with 0. But if everyone has 0, then we cannot transfer anything. Okay? So what do? Well, somehow we need to create money. All right, we'll talk about how in a moment. But let's say somehow we magically create money and we say a transaction was there was no input, but the output was Tanarak of 30 units. So I'll record that as a transaction. Let's think of that as this creation of money. How do we create money nowadays? How do we create it in the past? Anyone from America here? What did you do before? What did the Americans, and you see it in movies or popular, what happened, I guess, in California, I don't know when, in the 1800s? A gold, so there was really a gold rush. People discovered gold. Okay, so what happened is that people found gold in the ground. What did they do? And other things, so they mined the gold. And then I guess what they would do is they take that piece of gold to a bank, and the bank puts into their account the value of that gold. Okay? I find a piece of gold in the ground, I take it to the bank, and the bank says, okay, this is worth $1,000. So now my account balance is $1,000. My account balance was initially zero, but I mined and found the gold, took it to the bank, and the bank treats that as some value of, say, $1,000. So this is this initial transaction of how we created money in the account. And there are other examples, but let's assume that's what we do and what we'll do in Bitcoin, that there's some process that we can create this initial money. And we'll treat that as a transaction, a special transaction where there's no input. We don't transfer money from someone's account, we just create it so that Tanarak gets 30, Pakini gets 45. 3 through to 6 are the same as 1 through to 4 here. I've just introduced these two transactions. In Bitcoin, we'll see later, these are referred to as coin-based transactions. These create new coins, create new money. And it happens via mining. So we'll come back to see how they work. So, now, if we assume all users start with 0 and we have a list of all transactions, then we know everyone's current balance. And if we know everyone's current balance, then we can do things like detect if someone's trying to spend more than they have. Okay? Which is the feature we want in a banking system or a payment system. So, we can think a bank stores this information. A bank, when you go and create an account at the bank, you deposit your 30 baht, then think of that as transaction 1. You put some cash into the account, so the account now has a balance of 30. It started at 0 when you created it, you deposited money, it's now 30. So they record that transaction. And they record all the transactions of transferring money from one account to others. Therefore, given this information, the bank knows what the current balances are. So the bank effectively records this log of transactions. We want a decentralized log of transactions. Instead of the bank records it, it's not recorded in one single place, but it's recorded everywhere by everyone. So we don't rely on the central bank. So we get a decentralized log of transactions. Instead of the bank storing this list of transactions, this list of transactions is stored by everyone. I have a copy, you have a copy. Everyone in the network has a copy of that list of same transactions. And we'll see the way that it works is that, let's say now we have a network of users who are going to use Bitcoin, for example. A group of people who want to use it. Then when you want to create a transaction, you want to pay someone, you create a transaction and tell everyone else that transaction. You inform everyone in the network, here's a transaction, transfer 5 from Steve to Tanarak. Then everyone else in the network will verify that transaction. And verifying means performing some checks, including making sure if it's a transaction for Steve paying Tanarak 5 units, to make sure that Steve has 5 units to pay. We should reject any transaction that overspends or double spends money. That is, if my balance is 10, then I should be able to make any transaction that is up to and including 10. I shouldn't be able to pay someone 11. Okay? So the verification of the transaction is done by other users in the network with respect to the previous transactions in the log. For example, if everyone knows this and then transaction 7 comes along, Steve pay Tanarak 20, everyone should verify that transaction and find no, it's not allowed because Steve doesn't have 20. But if transaction 7 is Steve pay Tanarak 5, then it should be allowed because I have more than 5 in my account. So a user creates a transaction. Everyone else in the network of users verifies that transaction. And if it's acceptable, if it's not rejected, then they add that to the log. Okay, so it's added to the end of the log and then distribute that updated log to everyone else. So that's Bitcoin. That's how it works. Users create transactions. There's one log of all transactions, but everyone has a copy. As a new transaction comes, then that people verify that it's valid and then add it to the log. There are a number of issues. Now we're in the internet and there's many users across the world trying to use this system. We need to get this log, the same log of transactions, to everyone in the network. It may mean that I have a log which is different from someone else. So we need to somehow reach a consensus that everyone agrees upon that same log. We want to do things like stop people changing past transactions. Okay? I shouldn't be able to go back and say, Steve sent 11 to Tanarak. I shouldn't later be able to go back and change 11 down to 9 and say I only sent 9 to him. So once a transaction is verified and added to the log, it shouldn't be able to be changed. And we shouldn't be allowed users to double spend. Double spend is if I have a balance of 7 and I make 2 transactions, both sending 3 to other people. Sorry, not 3, 4. Okay, if I send 4 to other people, that shouldn't be allowed. I'm spending my money more than I've got. Okay, 2 times 4 is 8, but I've only got 7. So I shouldn't allow that. So here's an example. We had our previous log of up to 6 transactions, and then there's a new transaction submitted to the system, to the network. Assume everyone knows these 6 transactions. We all know and agree upon them. And then a new user, in this case Pekini, creates a transaction saying send from Pekini to Tanarak 15 units. This transaction 7 is submitted to everyone else. Everyone else checks based upon the previous log, is this one allowed? And they determine yes, it's allowed. Why? Because Pekini has enough balance to transfer 15 out. If you check, she starts with 0, she has 45, she sends out 8. Note, in is the input account, who it comes from. So she's down to 37, she receives 10, she's up to 47, so she's allowed to send 15 out. She has a balance of 47, so this transaction is accepted. Okay? And it's added to the list. So we now have 7 transactions, and then I create a new transaction. I send it to everyone, and everyone checks. I want to send 10 to Tanarak, and you do the sums. If you see beforehand my balance was 7, if I try to send 10 to Tanarak, that transaction should be rejected. It is not added to the log. Okay? It fails. What if I go back and change transaction 6? Okay, so this one would be rejected. So we've got 7 in our log. What if I go back and somehow everyone's agreed upon these 7? 6 was accepted in the past. So this log, think of it as a large file recording all these transactions. Everyone has a copy. What if I could go back and change the values in the file and make everyone believe that? I change this one, I sent 11 to Tunarak, I go back and change it to 8. If I could do that, then my transaction to Tunarak would be accepted. Because if I change that to 8, you can calculate that I would now have a balance of 10. Okay. We shouldn't allow this. This should not be possible. You shouldn't be able to go back and change transactions which were previously accepted. Okay. So it should be just one record of all the accepted transactions. We need to prevent users from changing the past transactions. Okay. Now, all right, so that's one challenge we have. How do we do that? Well, we'll see what Bitcoin does is that the aim is to make sure that verifying transactions, when you verify that a transaction is valid, doing so requires a lot of effort. And that once one transaction is verified, it depends, the next transaction depends upon that. What Bitcoin will do to try and stop this is to make sure that to verify a new transaction, it requires some time or some effort on the part of people who verify, and that the subsequent transactions depend upon the previous one. What that means is that if I go and change this value, if I try to change it, it's just some data in a file, it's easy to change, but then I need to re-verify that transaction or get the network to re-verify it. And that takes effort. We'll see it takes computational effort. And the system is set up such that all subsequent transactions also would need to be re-verified. That is, this one would need to be re-verified. And we'll see that the Bitcoin is set up so that the verification requires some computational effort. You need your computer to compute something. And if I want to go back and change it, I would need to get either my computer or other people to recompute this one and recompute this one. The amount of effort it takes to recompute these transactions to make this change is usually too great. And there'll be other ways to, so that a lot of effort is needed to make this change. And it's too much effort to get some benefit from. So we'll see how that works. That'll make sense after we go through Bitcoin in some more depth. So we've just talked about transactions, nothing about what is a Bitcoin or what is this system. Any questions on transactions so far? Think of, we have an input account, where the money comes from, the amount that we want to send, and an output account where we want to send to. Okay. And we have a log of all transactions. Think of it simply as a large file. Every transaction is recorded in that file. And that file, everyone has a copy. I have a copy on my computer, you have a copy on your computer, and so on. And there's a communications network that when a new transaction is added, the file is updated. And everyone's file is updated. That's the idea. So let's see how Bitcoin implements this concept. So we can think of Bitcoin as a payment system, a way to pay people, to transfer money from one account to another. Sometimes called a cryptocurrency or a digital currency, and even other things. The unit of currency or the accounts is Bitcoin, usually lowercase b, or BTC. So the unit of currency of my bank account with Bangkok Bank is baht. The unit of currency of my bank in Australia is Australian dollars. The unit of currency in Bitcoin is Bitcoin, okay, or BTC. All payments are recorded as transactions, shortened as TXN. So everything's thought of as a transaction. And there's this, what's called a public ledger. which is just a long list of all transactions. This record of all the transactions that have occurred in the past. When a new transaction takes place, the user who creates that transaction sends it to everyone in the Bitcoin network. So there's a network of users. In practice, people run Bitcoin software on their computer, and when I create a new transaction, I want to send money to someone else, I distribute that transaction to everyone who's, or to the network. It's not necessarily everyone immediately, but you think of everyone else who's running the Bitcoin software. I distribute to everyone, and everyone else verifies and checks, is this transaction allowed? Is it accepted or rejected? And if it's accepted, it's added to this public ledger. It's added to the list of trusted transactions. Users are identified using public keys. So now the first use of cryptography. In my Bangkok bank, my account, I have an account number. It's got my name on it. So my account really identifies me. If someone wants to transfer money to my Bangkok bank account, what do they need? Usually just my account number. Okay, so if you want to send me money, I'll just give you my account number and you can send me money. Okay. In Bitcoin, users are identified using public keys. So each user has a key pair. Everyone has their own public and private key. If you want to send someone else money, you need to know their public key or some version of their public key. But you can have multiple key pairs. So I can create 1,000 of my own public keys. Okay? It's not restricted to one per person. I can have as many key pairs as I like. I just generate them. Easy to generate on your computer. So if I want someone to send me money, pay me for something, then I just advertise my public key. And when someone wants to send me money, they get my public key and they will use that as the destination, as who to send to. So think of accounts or users are identified using public keys. So on that, public keys. Yep.
Before a transaction is accepted, it will have to be verified by everyone on the network.
Yes, correct.
So it will take some time. Like there
Yes.
are millions of users on the network. So if I have a slow internet connection, it will take time for.
Right. So you're right. That is, I create a new transaction, pay someone 1,000 Bitcoin. Okay, that's the transaction. I'm going to transfer them some Bitcoin. Then that transaction is, I'm just talking generally, sent to everyone in the Bitcoin network and they verify it. The verification takes time. Okay, it takes some computational effort to verify. And therefore, the person I'm paying, so I submit that transaction to the network. It takes time to be sent across the network and also, more importantly, to be verified. And therefore, the person who I'm paying shouldn't believe that they've got the money until it's verified. Okay? Let's say I pay Sam 1 Bitcoin and he's going to do some work for me. So I create the transaction, I send it to the network, it's being verified. Sam shouldn't believe that he's got the money until it is verified. So yes, there's some delay from when the transaction is created until it should be trusted to be verified. It's not accepted instantly. So then the destination has to wait. Well, it's up to the destination as to how long to wait. If Sam trusts me and he knows that Steve's not going to create a transaction that is invalid, then when I tell him I've sent the transaction, then he may, even though it hasn't been verified, he may believe that he's got the money and do the work. But if I've never met Sam before, he doesn't trust me, and I send him an email, okay, transaction's been sent, then he may wait until there's some confirmation from the network. Okay, so how long do you wait depends upon how much do you trust the sender. Okay? And we'll talk about some rules as to how long to wait. So there are some some rules that your software will use to wait before, if you think now you use software to keep track of your account balance, it's called a wallet, that account balance will only be updated after some time, after the confirmation transaction. Yes, so we'll see the confirmation requires, we'll see that in a moment, or we'll see that later. Okay. How long to wait, or how many people to verify, we'll see that once we see what the verification actually is, because that's important. It could be in the order of tens of minutes, hours in practice, okay? And we'll see why. Back to our accounts or our identity. We have public keys. So each user can generate one or more public-private key pairs. Okay? So it's quite easy. The software will do it for you. And you don't need just one. You can have as many as you like. The public key, here's some numbers. The private key is 256 bits. The public key is 512 bits plus some extra header information. Not so relevant, not important. So, for example, coming back to our transactions, Steve has his public key, PUS, and his private key, PRS. Tanarak has his key pair, and maybe Pekini has multiple key pairs. The advantage of having multiple is that you can start to become anonymous. Okay? It can be more convenient, but also it's harder for people to track which transactions you were involved in. We'll see that at the end, how to be anonymous in Bitcoin. So let's say our 3 users have their own key pairs. I've generated them. The public keys are actually hashed, really for convenience. So I have a public key which is 256 bits. That value is run through a SHA-256 hash and then some other hash function, write MD160. And the output is a 160-bit value. Slightly shorter, a little bit more convenient to tell someone. But actually more convenient is that public key hash is encoded into a little bit easier format so that I can post it on my website or I can include it in an email easy. Because this public key hash, think of that as my account number. If you want to send me money, you need this value. If I write 160 bits in my email, it's likely I'll make a mistake and you'll send it to the wrong person. But so there's some way that the hash value is encoded, so this has some error checking so that it's hard to make mistakes in that value. This is a Bitcoin address. Let's bring up some examples. I think I've got one. Where? Just wait, I'll bring up an example. To search on a website. Just be patient. Okay. Just an example that has some hash values. So someone creates a private key, so there's an algorithm for creating your own key pair. So you get a private key, so an example value here, so you keep this value. This is encoded in a nice form so that it's actually a 256-bit value, which is encoded. And you can generate a public key from that. It uses an algorithm such that you just need to store your private key and later you can create your public key from that. And here's an example of a public key. It's quite long here. But then you take a hash of this value using SHA-256 and you get this. And then you take this value and apply this other hash algorithm, RIPE MD160, and you get 160 bits or in encoded form. So this is what's called the public key hash. That's what you can tell other people. Your private key, you keep private. There's some extra information added. Where'd we get to? They add some version to identify what version of the protocol being used. And apply some more operations, and I think we get down to the bottom, we get the address, like the one down the bottom here. Almost there. Apply some operations just to make it more convenient to use, and you get what's called a Bitcoin address. And that's what you may often see. If you want to transfer money to someone, you get some random looking string like this. It actually identifies or comes from a public key. So you want to transfer someone some money, that person has their public key, they apply some hashes on their public key and they get this address. They tell you this address and you send money to this address. Okay. So transactions. So addresses are public keys, or based upon public keys. Transactions, similar to our previous simple example, we have inputs, outputs, and an amount. In Bitcoin, so we have inputs, they identify where the Bitcoin comes from. And we actually may have multiple inputs. Normally with a transaction, one person sends to one other person, we think. But Bitcoin allows to send to multiple in a single transaction, and actually we'll see allow multiple inputs to send to multiple outputs. It's hard to explain until we go through, see how it works. There'll be some transaction ID, TXN ID. Some of this we'll explain through example. The input will include the sender's public key. Okay. I'm sending to someone else, I'll include my public key. And I will sign the transaction data. When I create a transaction to pay someone else, I must sign it. And we sign using my private key. Okay. And that way, when someone wants to verify the transaction, they know it came from me because it was signed with my private key. And they can verify it came from me because they have my public key. Okay, so we use our public key cryptography to sign. The outputs will show where we're sending to. So a transaction will be send this amount to someone else. We'll come back maybe through examples, see these exact fields. Let's go. Here's our example transactions from before. I think we've seen it before, but I've just changed the notation. Okay, we may have multiple outputs. So transaction 3 was Tanarak sends to Steve 5 units. But a special thing in Bitcoin is that every transaction must spend everything that comes in. Okay. That is, how's the example? Come back to one of the earlier slides. After transaction 2, what is Tanarak's balance? How much money does Tanarak have after transaction 2? after. So before 3, 4 and 5 have occurred, Tanarak has 30. Okay? So his balance is 30. When he performs a transaction, if we move into Bitcoin, he must spend all of that 30. The next transaction takes those 30 units, or 30 Bitcoins if we now deal in Bitcoins, and the next transaction has 30 coming in, and there'll be 30 going out. That's the rule in Bitcoin, that everything that comes in must come out. So in our old bank view, he had 30 coming in, only 5 went out to Steve. Where's the other 25 in this case? Who gets the other 25? Tanarak. That's his remaining balance. In Bitcoin, we must explicitly say that. Tanarak has 30. Transaction 3, he wants to spend. Input is all of his 30. The output, 5 to Steve, and the leftover goes back to himself. It's just a feature of every transaction. What comes in must go out. And the way to deal with that is just send it back to yourself. The change, if you don't want to spend it all, send it back to yourself. So that's this new thing that in from Tanarak, out to Steve 5 units or 5 Bitcoins, out to Tanarak 25. So his balance is now 25. He still has 25 Bitcoins. That's the way it's implemented. So these turn out to be our same 6 transactions as before. So Tanarak has 25 out and so on. I think this, and maybe easier to read on your handouts here, tries to capture those transactions that we've gone through, those 6 transactions. So we'll go through this and identify the notation that we start to use, and we'll see when we use Bitcoin. So these 6 transactions, TXN1, think of that as the ID for this transaction. So this rectangle I've showed, this was a special transaction. Nothing came in. This is where we created money. Okay. So there was no input. The output was 30 Bitcoins, and it was to Tanarak. And the notation I'm using, remember the destination address is actually a hash of a public key. So this was 30 Bitcoins to Tanarak, and I denote that as the hash of the public key, and the subscript here is T, Tanarak's public key. This transaction says that 30 Bitcoins goes to Tanarak. It's his public key, it identifies his account. This transaction 2 identifies 45 Bitcoin go to Pakini. P1, Pakini has multiple public keys she created, so P1 is one of her public keys. So hash of Pakini's public key identifies the destination address. Transaction 3, remember Tanarak wanted to send a 5 to Steve. So the input refers to the previous transaction. If Tanarak wants to spend money, he must have that money. And in Bitcoin, the record of logs, the record of transactions refers to the previous transactions. So here we say the input for this transaction was transaction 1. Because transaction 1 says that Tanarak has 30, so the input to transaction 3 refers to transaction 1. And we'll see some other information. The output will be 5 to Steve, so the hash of Steve's public key saying send 5 Bitcoins to Steve. And another output, send 25 to Tanarak. Think of that as the change. Tanarak has 30 Bitcoins. He wants to pay me 5 because I did some work. So he creates a transaction that pays Steve 5, so using my public key, my address, and the remaining 25, the change of that payment, he sends back to himself. So he still has 25 left because all transactions must spend what comes in. So we talk about the input to a transaction and the outputs. The outputs identify who it goes to and how much. The input identifies the transaction where the money came from, the bitcoins came from. And Tanarak has 30 bitcoins. How does he get to spend those 30? Why can't someone else spend it? Well, the output of transaction 1 included the public key of Tanarak. So for him to spend it, he includes his public key in this transaction and effectively signs all of this data using his private key. And someone can verify transaction 3. Transaction 3 includes Tanarak's public key. It points to transaction 1. Transaction 1 was paying Tanarak. Someone can verify this because they can check. Using the public key from transaction 1, we can verify the signature here. The only person who can sign this transaction is the person who has the private key T. And since it refers to transaction 1, which used public key T, this would be verified. Think of it another way. What if I wanted to spend Tanarak's money? Transaction 1 sent 30 to Tanarak. If I tried to create this transaction 3, I must sign it. I must sign it. I cannot sign it with Tanarak's private key. I would sign it with my own private key. If it was signed with my private key here, PRS, someone would then verify this and they would check. Transaction 1 was sent to PUT. But the signature uses something else. It doesn't verify. What they would do is actually use the public key, PUT, and then try and verify the signature, and it would fail because the signature, if I created this transaction, would be using PRS, and the verification they would use PUT, and if you try to decrypt using the wrong key, it will detect that. So this idea of referring to the previous transaction is a way to keep track that this person has that money to spend in this transaction. That's getting more confusing. Questions? Let's just look at transaction 1 and transaction 3.
When we have to hash the public key?
I think the hash of the public key here is just a convenience, really. It has some minor security benefit, but mainly for convenience, to keep it short, an address. But from a cryptographic standpoint, think of the public key. The hash also provides a better, improved chance that someone can not work back to the public key. If there's some flaw in mapping public keys back to private keys, it still is hard to go from the hash value back to the public key. But mainly for convenience there. Yep. Take a hash, get a unique specific value, shorter, and especially for addresses. But you're right, from a cryptographic point of view, think of it, this identifies the public key of Tanarak. So when someone verifies transaction 3, transaction 3 must be signed by Tanarak. Transaction 3 points to money that Tanarak owns, therefore for someone to spend it, they must have the private key. So, let's try another one. Transaction 4. Remember, transaction 2 was paying Pekini. It was sent to the public key of Pekini, P1 in fact in this case. Therefore, if Pekini wants to spend that money, she creates a transaction, TXN4. She creates this transaction referring to the one where she was paid money. And to prove that she is Pekini, she signs this using her private key. and someone can verify that it's the right private key because they know that transaction 2 used public key PUP1, and therefore it's signed using PRP1, it's verified to be matching. So this is an important part to say the person who created this transaction owns the private key corresponding to the public key that the previous transaction was sent to. Okay. This one sent to public key P1. To be able to spend that, you must have private key for P1. And that's what Pekini does here. She encrypts using the private key of P1 to prove to others that she owns, or she's the destination of the previous transaction. And then she specifies where to send this, 45 Bitcoin to. She sends 8 to Steve, identifying using the public key of Steve, and sends 37 to herself. That's the change. UTXO is an unspent transaction something. Okay, I can't remember. It's written, I think, somewhere on the slides. It's Bitcoin currently unspent. So at this point in time, after these 6 transactions, this 37 hasn't gone into another transaction yet. It may go later. So we see, let's follow through the last 2. Transaction 3, Tanarak sent 25 to himself. PUT is the destination. Therefore, transaction 5 refers to transaction 3, signed using PRT. If it was sent to PUT, it must be signed using PRT, the corresponding key in the key pair, to prove that Tanarak is allowed to spend this money. And he specifies sending 5 to Steve, 10 to Pekini, and 10 to himself. Remember, 10 plus 10 plus 5 matches the 25 from here. And then the last one, what was it? Steve received 5. We'll come to that in a moment. Let's recap. So we're starting to get into the technical detail of the structure of each transaction. The input refers to the previous transaction, and in fact the ID of the previous transaction. So TXN1 is the input to transaction 3. And remember, we may have multiple outputs. Here we have 1, 2, 3 outputs. So the input refers to which of those outputs. So I try to denote that as transaction 3, the input is transaction 1, specifically output 1 from transaction 1. Transaction 5, the input is transaction 3, specifically output 2. Okay, so think of it as an index. If we can have multiple outputs, the input refers to which of those outputs. And therefore we know that the amount coming in here is 25, because transaction 3, output 2, sent 25, and it's sent to Tanarak. Therefore we have 25 coming in, and it's signed using Tanarak's private key to prove that he's allowed to spend this. And he specifies 3 outputs. One of them, output 1, goes to Steve, PUS. So I create transaction 6, but here's a special case. There's 2 inputs. Transaction 5 sent 5 to Steve. Transaction 4 sent 8 to Steve, so that's 13 in total. So there's 13 coming in to transaction 6. 5 from this transaction, 8 from this transaction, 13 in. And I pay 11 to Tanarak and 2 to myself. The change goes back to me. So it's like I've got 13 Bitcoins, I give 11 to Tanarak, and the change, the 2 remaining, is kept for me. That's what this sent to myself is. And it was signed using my private key, proving that I'm allowed to spend because the previous transactions referred to my public key. Almost there. Your question, what is an unconfirmed transaction? What's the O? Someone will find out later. After these 6 transactions, how much do I have? What's my balance? 7. If you remember back to the old example, it's 7. It's the same. Where does it, my balance? Well, look at these UTXOs. That's your current balance. This transaction, unspent currently, is 5 units to Steve, 5 bitcoins to Steve. So I've got 5 here, and this is to someone else, Bikini, this is to Bikini, this is to Tanarak, and I have another 2 here, unspent. So I have 7. So my wallet would show that my current balance is 7 bitcoin. So it's the sum of all the unspent transactions. Of course, I may create a new transaction that starts to spend that. And I would specify the inputs and who would I send it to. So this is starting to introduce the structure of each transaction and also some of the concepts of, well, we sign transactions. Transaction is, think of bitcoins are sent to someone's public key. To be able to spend it, you must prove that you have the corresponding private key. And you do so by encrypting with your private key. You sign. For someone to verify this transaction, what do? Transaction 3, how do they verify it? Going back to our basics, people create transactions and they send them to everyone in the network. So these rectangles, think as my computer creates this, creates some data structure, some message with this information, broadcast to everyone in the network. Then everyone verifies that transaction. How would you verify transaction 3? How would you check that it's allowed? Assuming, all right, forget about 4, 5 and 6, assuming transactions 1 and 2 have already been verified, they are in the log, then you receive transaction 3, how would you verify it? What would you do? Verify the signature. Okay, so what you would do is say, okay, transaction 3 says it comes from transaction 1. So what you would do is check the log. And you'd see transaction 1 was to public key T, to Tanarak. That's already been verified. Tanarak received 30. So this transaction refers to that. So what I do to verify now is I note the signature. The signature, and I haven't explained it yet, but we take all of this data in the transaction, we hash it to get it small, and we encrypt it with a private key. That's the signature of the data. To verify that signature, someone uses the public key of Tanarak from transaction 1, decrypts this. If it was encrypted with Tanarak's private key, it can be decrypted with Tanarak's public key, and then compares the hash of this data with the value included here. And if they match, everything's okay. But if I tried to create this transaction, if I tried to spend Tanarak's money, I would have encrypted with Steve's private key, PRS. If this was encrypted with PRS, then when someone verifies, they will use Tanarak's public key to decrypt. If it's encrypted with Steve's private key and try to decrypt with Tanarak's public key, you'll get an error. The decryption will not work, and it will recognise that. Okay? So that's how we verify the transaction, by using the public key of the inputs to confirm that, yeah, it is Tanarak spending this money. Because the only person who has the private key to sign this is Tanarak. No one else should have it. And of course, the other part of the verification is making sure the amounts match. That is, okay, he's not spending more than he got in the previous one. That's quite easy to check. So you check the signature and check that the amounts match.
Verify the last transaction for verifying?
That assumed, so that example assumed transaction 1 was verified by someone else. So remember, at some point in time we have a list of transactions which have been verified. Assuming the first one was verified at the very start when Bitcoin started, then assuming one's verified or some are verified, then the new transaction is verified with respect to all of them. Okay, so in this case, assuming 1 and 2 are true, are valid, then we can verify 3. So now we have 1, 2 and 3 being valid. Right? We can verify 4 when they're in our log of transactions. We can verify 5 because 5 refers to 3. 3 went to the public key of Tunarak. It was signed using the private key of Tunarak. That passes the verification. 3 sent 25 to Tunarak. 25 coming in, 25 goes out. If he tried to send more than 25 out, it would fail. Okay, the verification would not work. If there was 25 in and 26 out, someone would detect that. So then this would be verified, then eventually this one can be verified if the previous ones are verified. And we keep building up the log of verified transactions. Okay. So in fact, in Bitcoin, all transactions are recorded and logged from the very first. And I started at this website and we saw transactions being recorded on the website. We'll come back to that later. Each transaction you can have, I don't know if there's a limit on the number of inputs and outputs, but you can have multiple. Normally just one input, one output. But you can have multiple inputs. Maybe there's the software has a limit, okay, based on the data structure of the number of inputs and outputs, but typically you have multiple. And you can have a special case, these first two, no inputs. This is the creation of money. And we need to get to that. This is the concept of mining. Somehow someone creates money and it goes out to someone. So it depends on where your money comes from as to how many inputs and who you're sending to as to how many outputs. So by verifying transactions, we prove that the person who's creating this transaction is allowed to spend that money. Okay. Verifying transaction 3 proves that Tunarak is allowed to spend 30 Bitcoin because it corresponds to the 30 Bitcoin he just received. And then subsequent transactions can be proved or verified based upon that previous one. Any questions before we shift from this slide? This is maybe the main one. You're not spending any Bitcoins, are you? No. We'll see it, how much people are spending shortly. What have we got left? A fair bit. Let me just have a look before we have a break. Okay, a couple more slides. So that's the basics. Again, there's one big log of all transactions so far. Every transaction is recorded. As we verify them, we add the new transactions to that log. And the way that it works is that everyone who's running the Bitcoin software keeps a record of these transactions. And when I create a new one, let's say I create transaction 7 to pay someone, I create it and send it across the internet to everyone else who's using Bitcoin. And then they go to work to verify that transaction. And once it's verified, it's added to the log, and then subsequent transactions are keep added and added. And the log is updated. So we can think everyone has a copy of all transactions. We'll get to the point that the verification to stop people from cheating will need to take some effort, some computational effort. The next concept, So a sender, the creator of the transaction, the one who wants to spend the money, broadcasts that transaction to the network. The others in the network validate the transaction, check that I was the person who's had the money in the first place, and check that the right amounts are used. So use the hash of the public key and check the signature. And once it's validated, they add new transactions to this public ledger, this public list of all transactions. Now, there's this new thing that this verification of adding transactions to this record of existing ones are done in blocks or groups of transactions. We don't do one at a time. We'll see that we can group a set of transactions into a block, and there's some operation on that block that must be performed before all of those transactions are added to the log. Okay, so now instead of doing per transaction, we actually group a set of transactions and then operate on them. So called a block. And we'll see why in a moment. So one or more transactions are grouped into a block. Usually it's more, usually it's hundreds of transactions are grouped into one block. The block, so instead of a pure transaction log, we now have a block log. Instead of listing all transactions, we have a list of all blocks, and those blocks include the transactions. We'll see blocks, I think, the details of them. We'll see the details in a moment. What do we want to say here? So a block refers to some transactions, and we'll see that once a block is verified, then all those transactions are verified or confirmed. And then we actually have a chain of, or a list of blocks. The very first block contains the very first transactions using Bitcoin. Once they were verified, then a new set of transactions that people submitted were verified in the second block. And that was added to the list of blocks. And then new transactions came and they were verified. So the transactions verified in a group, they are added to the block. And we build up a chain of blocks and we get this blockchain. So now we operate in not just one transaction, but usually a set of transactions, and call that a block. And the blockchain, because each block refers to the previous block, like a linked list. If you know about linked lists from programming, one refers to the previous element. It's the same with a blockchain. One block refers to the previous block. This is our public ledger. This is the record of all transactions, because every block contains records of transactions. So everything that's verified is added to the blockchain. So we'll see that referred to commonly. So when you see a blockchain, it means all verified transactions, but grouped into blocks. The challenge to make sure Bitcoin works correctly is to make sure that, because we have the internet, everyone has their own computers doing this verification. One challenge is to make sure everyone has the same view of all transactions being verified. Because if one person thinks these transactions are verified and another person thinks a different set of transactions are verified, we can start to get errors. And we can start to get cheating where one person verifies transactions that says Steve spent 5 of his 6 Bitcoin, and another person verifies a transaction saying Steve spent 3 of his 6 Bitcoin to someone else. And we get what's called double spending, that one transaction says I spent 3 to Tunarak, another one says I spent 5 to Bikini. I only had 6 to start with. If both of those transactions are verified, then it says I spent 8 of my 6 Bitcoin, which is wrong and not allowed. So we must make sure that the transactions sort of are done in the right order. That is, if one is verified that it says I spent 5 of my 6, then the next transaction where I spend 3 of my 6 is rejected. if people have different views of which transactions have been verified, then this problem arises. So we must make sure that everyone has the same view of which transactions have been verified. Yep.
We do the transaction, should wait for one transaction finish, after that another one do it?
So how to do that is that you transact one transaction, after that's finished, then verify others. Remember, it's a distributed system. And what's happening is that I create 2 transactions. Send 5 bitcoins to Bikini, send 3 to Tanarak. And I send them through the Bitcoin network, but I send them in such the way that one of them goes sort of to this area of the network in the internet. So these people start to verify that transaction. And the other one goes to this group of people and they start to verify this one. And they don't know about the other transaction. Okay? It's a distributed system and not everyone has a complete view of what's happening. So that's the problem, that this group are trying to verify one transaction that spends my bitcoins, where another group are verifying a different one. If they both are verified, then I spent more money than I had. We want to stop that. So if we have a bank and there's a single entity that verifies all transactions, then you can do what you say is you do one after another. But in a distributed system where there's entities everywhere doing things independently, then we cannot control that. Okay. How we control it is we make sure that the verification takes some effort. And some effort such that, okay, these people verify one transaction. If this group verify the other one, then eventually that will be detected, and then eventually we'll reject one of those. And that's where the blockchain comes in. That's making sure all... So if we do get that case, and we can get that case where 2 people or 2 transactions are verified which are wrong, then there's quite a simple way to remove one of them. So instead of talking about verifying transactions, now we'll talk about verifying blocks of transactions, a group at a time. And that will move to here. And I'll just introduce it, then have a break. So now, verifying transactions. We group transactions into a block. And to verify that group of transactions, they create a block and they must prove that they did some effort. They spent some effort to verify that. And the basic way to do that is to get them to do some calculations that take time on computers. And we'll see that the system in Bitcoin is set up that the creation or the verification of an individual block takes about 10 minutes. What takes 10 minutes on your computer? Well, we'll see that we can make calculation of hash values to take time and set the problem such that on average it will take about 10 minutes. It doesn't matter how fast a computer is. We'll set a problem such that it takes about 10 minutes to solve that problem. And the idea is that it takes 10 minutes of fast processing. The idea that one person will create, if we have 2 different groups trying to verify different transactions, one of them will win. One of them will verify this transaction first. Then they'll tell the others saying, we just verified this transaction. So coming back to this case, Steve had 2 transactions, trying to double spend his money. This group is trying to verify one of his transactions, this group trying to verify the other. It takes time to do that. Turns out, by luck, or these people have faster computers, they verify one of them first. Once they verify, they tell everyone it's verified. This group who was trying to verify the second one, they realise one was previously verified, therefore they stop working on this one because they see it's wrong. So we introduce this timing in there. And it turns out in practice, even with delays across the internet, in practice, there are very, very few cases when two groups of transactions are verified at the same time. Okay? Because the verification requires some computational effort, and it turns out in most cases, if two groups of people are working on verifying different sets of transactions, one of them will get there first and tell the others, and the others will stop. So that introduces this ordering into the system. It's possible in theory that they both finish at the same time, but even then, the next case of verifying transactions will identify and reject one of them. Okay. Let's stop for five minutes, answer any questions.